Share the screen. So today we move to another device, another electronic device, which is called the field effect transistor. Now there is obviously some difference to the bipolar junction transistor, difference in terms of construction. At the very root level the difference is there, that's why it is a new device. So how the construction is different than the bipolar junction transistor? In the bipolar junction transistor, if you remember, there were a PNP or an NPN, so different layers of semiconductors, different layers of extrinsic semiconductors were there, and there were two junctions. There were two junctions, and which gave rise to the phenomenon of the bipolar junction transistor. So there were also another important thing was that in the bipolar junction transistor, both the electrons and the holes formed the majority carriers. So because there were these three regions where in the N region the electrons were the majority carriers, free electrons. In the P region the holes were the majority carriers, and both together gave rise to the effect of the current within the BJT. So that is why it was called bipolar, because bipolar means both polarities are present, both the electron and the holes are present in the bipolar junction transistor. However, in this one field effect transistor, there is only one type of majority carrier which produces the current. As such, it is simply an N or a P semiconductor, either an N type semiconductor or a P type semiconductor, which forms the main body of the transistor. Now you know that if we just simply put up a voltage source across this semiconductor, then it behaves just like a resistor. Just like a resistance is there, it behaves in that manner. But we need some additional properties we wish to have from it. So what we introduce a layer of or a region. It's not a layer as such, because layer means the entire layer like this, but it is not a layer, it is a region of P type semiconductor is introduced here. So the doping is done in such a way that the majority part is N, but at the very sides there is a small region of P type semiconductor. It can be also the opposite, that means the main body can be a P type semiconductor and this could be a N type. So both are possible, but what we would study here is this one, where the body is a N type semiconductor, and if it is a P type one, then biasing and etc., all those things would be simply the opposite. But normally we are studying this one, and availability is also normally this is available in packages also. So this is what we are going to study. Now what happens now in this P region, there is another terminal which is connected to this P region, and this terminal is called the gate terminal. This terminal is called the gate terminal, and the other two terminals which are on the body of the N type semiconductor at the two ends, they are called the drain and the source. Now which end is the drain and which end is the source? There is a slight difference in manufacturing, but during our normal operations, that means when we are dealing with frequency signals within normal frequency regions, the source and the drain really doesn't matter. Which side is the source and which side is the drain, it doesn't matter. Okay, so either side, any side you can consider the source or the drain when you are doing normal operations. However, in very high frequency operation, the drain side and the source side, there is a slight difference which we need to take care, but right now we don't need to be so much bothered with that. So so now there are these three terminals. So this is also a 3-terminal device. There are 3 terminals: drain, source and gate. And the normal biasing happens in this way. You can see between the drain and source there is a positive voltage between the drain and the source. So the drain side is positive and the source side is negative. So suppose this gate was, this P region was not there, like when it is in this manner, then what happens? This is able to drive this positive side is pulling the electrons this way. So a current is getting driven in this way. So the current, there is a current in this direction, right? So a current is in this direction. Here also a current would be in this direction, but obviously some effect of this particular biasing would we would be able to notice on the current. So how this VGG, this bias, how this bias influences the current, that is our first thing that we should try to understand. Now before even going there, just notice this thing, that this biasing is basically the biasing between the gate and the source. The gate and the source. So the gate source is biased. So between the, if you just consider the gate and the source as the terminals, then you are seeing a P region and a N region. So there is only a single depletion region or a single barrier here. Single junction is there. So what is a single junction device? That is a diode. Diode we have already studied. And if this is considered as a diode, then this biasing is a forward biasing or a reverse biasing? It is a reverse biasing. The reverse biasing of this gate source diode has been done. This is done intentionally. Please remember this biasing is intentional. So we have to reverse bias the gate source junction. When the gate source junction is reverse biased, that means what? That means, first thing, that means there is no current in this particular loop. In this loop there is current, but in this loop there is no current. So Ig is always 0. Very important to note. Ig is always 0. In bipolar junction transistor we had some IB, some level of IB was there, and it had to be there because ultimately the output current was some beta times the IB. IC was beta times IB. So in this case, of course, you can understand now that the current that is driven in the output, so this output loop, the current that is driven in this output loop is not a function of the input current, because there is no input current. So this output current is a function of the input voltage VGS. So this device is basically a voltage controlled current source. This is a voltage controlled current source. The bipolar junction transistor was a current controlled current source, but this one is a voltage controlled current source. Okay, the current would be controlled only by the gate source voltage VGS, not by the gate current, because there is no gate current. how this voltage is able to influence the current, the output current. This current is actually called ID, drain current. It's called the drain current mostly. So how this is able to influence the drain current? Now just take one point in mind, that these are just nomenclatures: drain, gate, source. So you will see, you will observe that the nomenclatures may not make very common sense. Okay, make a common sense. So might not make common sense. So please don't bother about that. These are just nomenclatures. So just take them as they are given in the this conventions. So this is a conventional nomenclature, that's all. Because source, mainly we talk about the source, means the source voltage somewhere here, but that is not the source. The source is something here, and this is a drain. So why this is called source, why this is called drain, so those things we don't need to bother so much. Okay, so let us just go ahead and try to understand now how the VGS voltage is going to influence the current, drain current, through this FET, field effect transistor, is also known as FET. Junction field effect transistor is known as JFET, also known as JFET. JFET is also, it is called JFET. So now just one thing to note, that this gate source voltage can be 0 at the most, because it is always reverse biased. So it can be 0 at the most, and it can be negative. It can become negative, but at the most positive it is 0. Okay, so can we keep on increasing the negative value to any extent? These things actually matter the entire operation of the JFET. Let us see how things happen. So first let us consider the situation when the VGS is 0. That means this part is short circuited, the gate source is shorted. That is the highest value of VGS that we are allowing the device to have. Okay, so when the VGS is 0, then what happens? There is, see, because this is reverse biased, there is some this is the depletion layer. Depletion layer has been formed. Depletion layer, anyway, there is some depletion layer between the P and the N. The depletion layer is what? Depletion layer is that region where there is no majority carrier. No majority carrier is there in the depletion region. Now this depletion region is there to some extent, but here in the inside there is a passage through which the current can flow. So now VGS is 0, so your VDD here, this VDD has set up a VDS. So some VDS has been set up, drain to source voltage has been set up. So suppose the drain to source voltage is 2 volt, then what will happen? When the current flows from the source to the drain within the device, then we can assume that there are these resistances that are there within this device, and we can break the resistance into smaller parts of equal resistance. Okay, this is just a modeling, just to make you understand what phenomenon is happening inside. So just we can assume that this resistance has been broken down into smaller parts of equal values. So when the same current is flowing through these resistances, there is some drops getting developed. Some drops are appearing here. So what happens? This drop is the maximum. So this drop is the maximum, this drop is the minimum. Now you look here, this is an N region and this is a P region. This is the blue part is the N region and the light gray is the P region. So the P region is 0 volt and the N region is some positive value. Obviously this is reverse biased, but which part is more reverse biased? The top part is more reverse biased. More reverse bias means the depletion layer, the depletion region has increased. The depletion region, the thickness of the depletion region is more. So near the drain the depletion region is more and near the source the depletion region is less. So something like this we can draw. This happens, this phenomenon happens. The phenomenon is some variation in the depletion layer. When the current is flowing through the device, some variation in the depletion layer takes place. So now what we'll do, here you see the graph. This is the VDS ID graph. So that is what we are trying to understand, that when we change this voltage VDS, what happens to ID? That is, ID is this current, drain current. What happens to ID? That is what we are trying to understand in the situation when VGS is 0. So VGS is 0. Okay. So what happens? You have some VDS which is setting up this sort of potential difference. So always you will find that the barrier, that the depletion layer near the drain is larger in size than the source. So when you keep on increasing the VDS is getting increased here. The drain current is also increasing because it is nothing but a resistance. So the drain current is also increasing, but the depletion layer is also increasing. Depletion layer is also increasing, and at a certain value of VDS, which is called the VP or the pinch off voltage. Pinch off voltage. So you can write this down, pinch off voltage. You will also get this in the book. So at a certain value of VDS, which is called pinch off voltage, what happens? The depletion layers almost touch each other. Almost touch. There is a very small region, small passage which is left for the current to pass. Very small layer, very small area that is left through which the current can pass. After this, what happens? Because of this like constriction through which the current has to flow, the current does not increase any further. So even when you increase the VDS, the current does not increase any further. So once you cross the value of VP, the pinch off voltage, the current was increasing before that, but after the pinch off voltage the current does not increase any further. It comes to a saturation level. So this is the characteristic, looks almost very similar to what the collector characteristics we had seen for the BJT, and the same sort of behavior we are able to obtain from another device, but here we are only varying the voltage VGS, the gate source voltage is what we are actually the parameter, the input which we are which is influencing the output. Now in this case, in this particular curve, we have seen this particular curve appearing for VGS equal to 0. So we have to see what is the behavior for other values of VGS. Of course we have to see, but just let us understand this curve for VGS equals to 0 in a more detailed way. So what is this region before VP? This region is called the saturation region as earlier. Earlier also this region was called the saturation region. This level is called the saturation level and it is called IDSS. IDSS is the saturation value of ID when VGS is shorted. So there are two S, ID, saturation, shorted. So that is why IDSS. So this is the maximum value of drain current that can actually appear within the device. The device will not allow further more value of drain current. Device by its own nature does not allow any further increase in drain current. So this is the saturation maximum level of drain current and is called IDSS. This parameter is given in the data sheet of these devices. JFET devices, you will find an IDSS value given in the data sheet. This region you see, this region is the saturation region, also known as the ohmic region, because although there is some slight curve here, but we can approximately say that this is a straight line from this 0 point to VP IDSS point. So this point there is a straight line, and this gives rise to a resistance value in this region which is constant. So this ohmic resistance is RDS, which is VP by IDSS. This ohmic resistance is between the drain and the source, because the axis is, you see, VDS and ID, drain source voltage and drain current. So this is the ohmic resistance between drain and source, RDS, sometimes also known as RD. So RDS, why S? Because this is VGS is shorted, that is why it is S. It is the max, it is one value, it is the actually the lowest value of the resistance, because the current is the maximum. VP remains same, IDSS is maximum for this particular VGS equals to 0. For VGS, lower values of VGS, VP will remain same, but IDSS will be also lesser, also lower. So now we try to see what happens when we decrease the VGS value. So let us try to understand the phenomenon first from this diagram. So now let us suppose that there is some VDS, any VDS you assume, which is like higher, greater than VP, you can say is greater than VP. But then what happens when the VGS is getting increased, like it is more minus, then what happens, the barrier potential will increase, because we are having more reverse bias here. The barrier potential, the depletion layer is getting increased, and the lower regions are also getting thicker. These regions are also getting thicker when the VGS is more negative. This entire region is going more thicker. As you keep on decreasing this VGS, there will arrive a certain value of VGS for which the depletion layers will merge with each other, and that point this entire region will be devoid of any majority carrier. So what will happen? The current will drop down to 0. There will be no current ID. So of course you can understand that from VGS equals to 0 to a certain lower value of VGS, negative value of VGS, the current is actually decreasing, because we are taking out more and more majority carrier region from this place as we are decreasing the VGS value. As we are decreasing the VGS value, the depletion layer increases, that results in less amount of space for the majority carriers, so the current, ID current, also decreases. So this is the actually the different curves, different output curves for different values of VGS. So VGS equals to 0, this is the highest value of current that we can see, this is IDSS. For VGS equals to -1, you have some other saturation value of current which is less than IDSS. For VGS equals to -2, further less. In this way you can go till some VGS where you will experience no more value of current. This VGS is called the VGS off, or the gate cutoff voltage, which is written as VGS off. Name is gate cutoff voltage. So why this nomenclature? Because when you come to this voltage level, you don't have any current in the device, so it is cut off, the device is cut off. And this value, this VGS off, is same as minus Vp. So the pinch off voltage that we noticed here, this VGS off is also same as minus Vp. There is a minus sign involved here because the VGS off is a negative value. So please remember this, that the pinch off and the VGS off are same numerically, but with a negative sign it is coming for VGS off. As you can observe here, so just first let us understand what is the RD which is appearing. So RD is again the resistance between this of the slope between these two points, this point and this point, again for this point and this point. So this is the RD. So RD can be expressed like this: RDS divided by 1 minus VGS by Vp whole square. This VGS is only magnitude, because VGS is negative, so we only keep the magnitude. So it varies as in a like a square law, it varies. So RD is actually higher than RDS. So RDS is the least, and any other value of RD is more than RDS. So as we are decreasing the VGS, we are increasing the resistance of the device. We are increasing the drain resistance. So I hope that is clear here. And another thing, yes, here we are getting this. So you can also observe from this curve that when VGS is decreasing, we are decreasing VGS in steps of 1, but the current is not getting decreased in the same order. So VGS is getting decreased when it is decreased by 1, the current is getting decreased quite large, then a bit smaller like this. Or from the other direction, if we try to come, when we are increasing VGS by a single unit, the current is getting increased more and more when the VGS is also higher. So there is a nonlinear relationship between VGS and ID. In fact, that relationship is a square law relationship, and that is what we will see now in what is called the transconductance curve. So please remember this thing, that the JFET has two different curves. One is the ID VDS, which is the output characteristic, ID VDS, and another is the transconductance curve. Transconductance is neither the input curve nor the output curve. It has the input voltage and the output current. In BJT we saw the input characteristics, which was the IB and the VB, both were input side parameters, and the output characteristics, which are the IC and the VC, which were the output side parameters. Here also this is the output characteristic, because ID and VDS both are output side current and voltage. This one is ID VGS. Now ID is output current, but VGS is input voltage. So that is why it is called transconductance curve. It is like a conductance because ID versus VGS, but it is a transferred conductance. it is transferred from the input side to the output side. That is why it is called transconductive curve. So when we plot the VGS with the saturation value of ID, we are plotting the saturated values. So in this region where the ID has saturated, this is called the active region, by the way. In the same manner, so this was a saturation region, this is the active region. In the active region you have the saturated value of ID. So there is some you have to understand that these nomenclatures are not very not so much ringing to our common sense, but the saturated value appears at the active region, and in the saturation region the current is increasing. Okay. So anyway, so here we are dealing with the VGS and ID values in the saturation region, the saturated values of ID in the active region. So those are we are plotting. So when we are plotting that, of course the entire curve is in the left half, because VGS is not there, is not more than 0. So it is 0 and less than 0. So suppose our pinch off value is minus 4. So from here we start. So at the pinch off value the current is 0, and at VGS equals to 0 the current is IDSS. So these 2 points we can get readily, but the intermediate points that we have to find out from the output characteristics. From here we see at minus 3 it is 0.625, at minus 2 it is 2.5, minus 1 it is 5.62. So when we plot these things, these points we get, and then we join these. So when we do the experiment and we join this plot is coming out as nonlinear, and we can also find out a relationship which is very easy. It is nothing but a squared law that we see, nothing but a squared law. The law is this, that ID is IDSS, any ID which is lower than IDSS can be given as IDSS 1 minus VGS by VP whole square. Now VGS by VP is the maximum value of VGS, minus 4 is plus 4, VP is plus 4, and VGS is some value between 0 and 4. So this is less than 1, that means IDSS is less than ID, and it decreases in a square manner. As you can notice one thing here, that so this is a normalized transconductance curve. What is normalized curve? Normalized curve means you divide the axis values with their maximum values. So IDSS is the maximum value and VGS off is the maximum value. So we divide the current axis by IDSS and the voltage axis by VGS off. What does this mean? The extreme points become 1. The extreme points become 1, and the internal points are just ratios, and this reveals something. Actually this reveals the picture of how the ID and VGS is operating. So you can see that when VGS is half the value of VGS off, when VGS is half the value of VGS off, then ID is 1/4 the value of IDSS. ID is 1/4 the value of IDSS. This normalized transconductance curve would remain the same for any device, because it has to follow this equation, and this curve appears from this equation. For a particular JFET to JFET, this IDSS, VGS off, this will vary. So the exact values will vary, but the normalized curve will remain the same. So this is the importance of normalized curves. In many other places also you will find normalized curves. In normalized curves, the maximum, it is divided by the maximum values, and these maximum values will differ from one particular object to another particular object, but the normalized curve remains same. So it is easier to work, or more general it is to work with normalized curves. So anyway, this completes almost the understanding of JFET. So I hope you understood why the JFET is a voltage controlled current source, why Ig is 0. This is very important to remember. Ig is 0, and Ig is 0 means that there is the input impedance is very high. Actually, this is what it means. Of course, there will be some Ig might be there, but it is like, it is not negligible, it is beyond negligible, it is 0, you can say. There is, so the impedance is very high, almost hundreds of mega ohms. So whatever voltage you give here, it doesn't matter, nothing comes through this channel. So these are the some characteristics of the JFET which are not found in BJT. Very high input impedance, gate current is 0, it is a voltage controlled current source. Okay, the current, there is a saturated current at various levels of VGS, and the dependency is not a very direct dependency like beta and all. The dependency is in this manner, in a square law manner. Okay, so it is not a linear, not really a linear thing happening here. Okay, so the idea of pinch of voltage, the pinch of voltage, what is the pinch of voltage, why these depletion layers are increasing. So all these are ideas which you need to be very clear about. This gate cutoff voltage is given in your specification list also. So in the data sheet you will find the gate cutoff voltage. So once we know all these things, now we have to see the different biasings, different bias configurations of the JFET. First bias is simple gate bias. Here what we are doing, we are making the source connect to ground, and in the at the gate we are giving a negative potential through some resistance. Okay, so since there is no current here, this minus VGG is appearing here. Okay, in this, at this point, and so for this there will be some drain current getting set up. Some drain current would be set up in this channel, and it is very easy to see that the equation at the output side would be nothing but this one. This is a simple KVL equation. VD is the drain voltage, VD here, equals to VDD minus IDRD. That is the thing. And when this is the case in the gate bias, so one can basically, so since there is no current in this branch, the only current flows in this particular branch, one can simply replace this entire thing by this particular circuit, where the RD is there and the JFET is replaced by RDS. JFET is replaced by RDS, which is the drain to source resistance. Now normally we use this particular biasing to set up the Q point in the saturation region. We normally use this type of biasing to set up the Q point in the saturation region. And how do we do that? So this is the actually the load line. This equation will give the load line. So the load line you can readily obtain by making this VD is nothing but VDS actually, because VS is 0. So this VD is nothing but VDS. So this is VDS. So now you see, you can simply draw this load line by using this VDD point here, and when your VD is 0, you have VDD by this ID saturation. So this point you get some ID value you get, which is VDD by RD. Now this VDD by RD is referred to as ID sat in this case, and this will intersect the actual output characteristic curve at some point. And what is this point? So you please remember that the ID is flowing through this resistance RD. So the voltage of this point is ID RDS. The voltage of this point is ID RDS. Okay. So this thing, this voltage has to be less than the pinch off voltage. That is one thing we should ensure to keep the Q point in the saturation region. In another way, we can say that we have given this VGS as 0 voltage. At the very beginning we said VGS as 0. Then whatever you get the current, that current has to be less than IDSS. The current that you get has to be less than IDSS. Then it will be very sure that it is in the saturation region, because once you are in this part, the IDSS all the load lines which will give you a current which is less than IDSS will be in the saturation region. So whatever VDD by RD you will get, that must be less than IDSS, and it has to be much less. Actually we keep much less. So this load line is very flat in this region if we are trying to make a hard saturation. And how do we ensure the hard saturation? Because we have a handle on this RD. This RD is something that we can set. So if we increase this RD, of course this ID sat will become lower and lower. So we can ensure that we are in the hard saturation region. So when this type of biasing is used, when we wish to have the operation either in the saturation region or in the cutoff region. So when it will be in the cutoff region, when we will make this VGG more than the pinch off voltage. So whenever VGG is more than the pinch off voltage, or this voltage is more than the VGS cutoff, then it will come to cutoff region. And if you give it as 0, then if RD is maintained to a high value, then it will be in the saturation region. So in this way we can utilize the gate bias to use the JFET as a electronic switch. JFET as a electronic switch, and when it is on, then there is a resistance RDS which we can calculate by using the formula given above. So this is actually the RDS, this is the RDS S, you can say. So 1 minus VGS by VP whole square. So whatever value, actually we are using VGS equals to 0, so RDS is VP by IDSS. This is the value because we are using VGS equals to 0. So we are having the resistance as RDS, VP by IDSS. And when it is in the cutoff region, of course this is open. So from self bias we will start, we will go on Friday. Okay, so Friday we will covered starting from self bias. So today we have covered till gate bias and the basic JFET, how it works, the basic physics behind it. So that we have covered. So just go once through all these things. There is one day in between. So just have a brief study in the book. Do some self study about JFET. JFET is a lot easier than BJT as per what it feels to me, but like it is like person to person it might vary, but you can just go through the book and try to understand in some more detail. There are a lot of other information about the differences between JFET and BJT given in the book, so you can see there, you can look it up from there. So today we'll end here, and if there are any doubts in any of the understanding that we did today till gate bias, you can ask right away. Otherwise we can close the meeting. So is it okay? So I hope there is no more doubts. People are already started to leave. So let me end the meeting now, end the recording, end the meeting. Thank you.